So today we're talking about some extremal problems on graphs. And by extremal, I mean that we want to just make some condition, and we want to fix the number of vertices on the graph and try to find the number of the minimal number of edges or maximal number of edges which satisfies this condition. So I want to find the minimal, maximal, yes, number of edges satisfying this condition. And we also have some results of this kind. So for example, if we have for example, if the degree of each vertex is less than 2, then of course we have cycles. So for example, if for all vertices the degree of this vertex is more or equal than 2, then there exists a cycle in graph G. And so this is the bounded inequalities, because if we assume that we have 2 vertices of degree 1, then we can provide a graph where all degrees is more or equal than 1 except for 2 vertices, and there we have no cycle. It's just an example of just simple path. And if we usually we just fix some graph H, some graph, and we want to find the some kind of restriction of number of edges such that we can guarantee that our graph contains the subgraph isomorphic to isomorphic to H, and so we can find the x of nh as minimal number of edges such that it is guarantee that we have maybe I don't no, maybe I don't, I need to make a little definition here. Yeah, so maybe it's not minimal but maximal, and right that we don't have that there exists graph G on n vertices without subgraph isomorphic to H. So we try to find this called Extremal because we want to find the maximal number. So of course, if we have all the edges, then of course we have subgraph isomorphic to H. But then we just cut out some edges, and then we talk. If we count out the minimum number of edges, then we have the maximum number of edges, such that there exists some graph G on n vertices without subgraph isomorphic to H. Okay, what kind of graph H we can take? The simplest graph is just the simplest type of graph is just one edge, and there is a easy problem. So of course, if you have one edge, then of course we have subgraph isomorphic to H. So this is 0, will be 0. So if you have one, yeah, with okay. So if you take the first non-trivial example, will be triangle. So I want to ask, so what, how maximal of edges can graph on n vertices have, such that it doesn't contain triangles. So I want to have graph on n vertices without triangle. Subgraph triangle is just a subgraph isomorphic to case 3. So how many edges can graph G have? So can we have the upper bound on the number of edges? Of course, lower bound is 0. We can have no 0 edges, and we have no triangles. But if we take too much edges, for example, if you take and choose 2 edges, then it will be complete graph, and of course, it will contain many triangles. So somewhere between 0 and choose 2, there exists some estimate upper bound of the number of edges, such that we have some extremal graph which don't have triangles, and if we add one or one edge more, there of course will be triangle. So the question is, what is this number, and what is the picture of the maximal graph which doesn't contain any triangle at all? So you can just so this is the problem. You can just think of it and try to draw a picture, and I will give you like 3 or 4 minutes, and then we'll explain how can we prove that this is the estimate bound, yeah, upper bound. Okay, someone has any ideas? Maybe some ideas of what is the number of edges in G? Yeah, and the example of the graph without triangles. Sorry? Yeah, I mean example of graph with edges of n squared over 4 such that there is no triangles in it. Maybe someone in Zoom can provide an example which have n squared over 4 edges and don't have triangles. Можно чат больше сделать? N equal 4. Okay, for n equal 4, but I mean that the example is the same for each n. Okay, so of course, for odd n we don't have estimate number of n squared over 4, but we can just take the integer part of it. So for maybe for even n, can we have for even n provide an example of graph without triangles which have n squared over 4 edges? Can you explain what is the graph? So for example, n equal to 10. Can we construct a graph with 25 edges? 10 squared over 4 with 25 edges without triangles.
Sorry, but how did we get n square over 4?
It's just a suggestion from fun. Yeah, fun. From fun. Yeah, okay, so do you have any other suggestions about the number of edges?
N plus 2?
And plus 2 is not too much. We need to have some. It's good to have n squared times something because we need to have no linear function but quadratic function of the n.
Sorry, is it possible to explain the question again?
Okay, I want to suggest I consider only graphs without triangles. What is the maximal possible edges can this graph have? So so suppose we'll consider all the graph on n vertices, for example 10. We have consider all the graph on 10 vertices, but without triangles in it. So we don't have graph isomorphic to H. The question is, what is the maximal number of edges that we can have in this graph without triangles? Of course, if we have n choose 2 edges, it means that graph is a complete graph Kn, and it's of course contains triangle. And of course, if we have 0 edges or n edges, of course we can provide a graph without triangles. But can we find the maximal number of edges such that there is no triangles in this graph? Okay, so maybe you don't have. So this is the this is the right answer, n squared over 4. But I suppose if Fan suggested that maybe he can construct the graph. But if you don't have any ideas how to construct it, let's try to do some research. So let's take this graph with maximal number of edges such that this don't have triangles. So suppose we have graph G on n vertices without triangle and with maximal number of edges and with maximal number of edges. So if we add one more edge, then this graph will contain the triangle. Okay. Of course, we have some edges in there. Let's consider some edge. So we have node V1, V2. We have an edge between them. Okay, can we? And we have other n minus 2 vertices. How many edges between? Can we calculate how many edges can be between V1, V2, and other n minus 2 nodes? So can we have some restriction of the number of edges between V1, V2, and other edges of other vertices of this graph? Two times n minus 2. Yeah, so of course it doesn't, it can have triangles. It means that these two vertices can have common neighbor. So they cannot connect it to the same vertex here. So it cannot have this situation where they have some vertex V with the edges V1V and V2V. It means that each of them connected to the different vertices into this remaining graph. So it means that if we don't have triangles, then we have maximal n minus 2 edges between V1, V2 and other graph, the remaining part of the graph. So V1 connected to some edges here, V2 connected to some edges here, and of course, if there nodes that don't connect to V1 or V2, then of course we can connect them with V1 or V2, and we don't have any triangles. Yeah, no, but maybe we have. Yeah, so maybe they have, but now I have a restriction. If I take any nodes we have edge between them, it means that they connect with the other graph using not more than n minus 2 edges. So if we consider graph without V1 and V2, it will have no triangles. It contains n minus 2 vertices, and we cannot add more to, so, and we have restrictions that edge of number of edges in graph G. So we have one edge E here and no more than n minus 2 edges here. So we have this inequality here. Yeah? So if we take this graph, this new graph, and then we calculate all the edges outside this subgraph, then we'll have n minus, not more than n minus 2 edges coming from V1 and V2, and one edge between V1 and V2. So we have this inequality. And this new graph has n minus 2 vertices. So if we can prove by induction that E of new graph is not greater than n squared over 4, so we can just see that E of G is not greater than n minus 1 plus n minus 2 squared over 4. Then this is n squared minus 4n plus 4 over 4, which is n squared, plus n minus 1, which is n squared over 4, minus n plus 1, plus n minus 1, which is n squared over 4. So we can, if we know by induction that this holds for graph G on n vertices, then we can prove it for graph G on n plus 2 vertices. So maybe, yeah. So if I can prove that E of G is not greater than n squared over 4, then I can prove that E of G on n plus 2 vertices also has this restriction. So we just need to check if the base of induction, and base of induction will be, I don't know, maybe for n equal 1, 2, 3, we can check that if we have no triangle, then on 1 we can have just one vertex, on n2 we have one edge, on n3 we have two edges, and so here we'll have not greater than n squared over 4. Here we have 2 squared over 4, which is 1, and 3 squared over 4, we will have 2.5, and so we'll have all these inequalities here. Okay? But we also want to find if it's the good restriction. So if we can provide the graph on n vertices such that it has no triangles, and it has n squared over 4 edges. Did someone suggest in some maybe an example? So maybe we'll start from small n. So for example, n equal 2. So for example, n equals 3, we'll provide this example. Maybe we want to find the graph on 4 vertices with number of edges equal to n squared over 4, which is 4. Okay, can we provide the graph on 4 vertices with 4 edges without triangles? And then on 6 vertices, it will have 9 edges. And on n vertices, it will have 16, yes. Yeah, just square and m squared, yeah. Can you provide the examples of this graph without triangles? Can someone do it? Yeah, so for the first one, it's just T4. We can just take the cycle on 4 vertices. But for which graph on 6 vertices, 9 edges, and don't have any triangles inside it? C6 and all the diagonals. Yeah. So you just, I think you were suggesting something like this in arbitrary case. But before you continue, I just suppose that we can see that if you take this graph on 6 vertices, it has simple structure. You have 3 vertices of like some even vertices and some 3 odd vertices, and you see that all even vertices, so red vertices connect to the blue vertex and vice versa. So this is more if you can redraw it in more maybe helpful with, we just take the bipartite graph K33, and we see that if we provide full bipartite graph, so we have two parts, and we connected all edges between them. Then, of course, this graph has no triangles because the vertices in each of the parts don't connect to each other. We already discussed that you don't have cycles of length 3, only cycles of even lengths. So we have minimal number of edges in cycles is 4. And so, for example, for this guy, we can have K4, and for graph on n vertices, we can have Kn over 2 and over 2. So if we take two different parts containing n over 2 vertices and provide all the edges between them, then the number of edges will be exactly n over 2 times n over 2, which is n squared over 4, and we don't have triangles. And for the if n is odd, then we need to take one part will be n squared plus 1, second part will be n squared something like this, I suppose. And so we will have a little bit, so we will have the integer part of n squared over 4. I suppose we'll have n squared over 4 minus 1 over 4 edges, which is just exactly the integer part of n squared over 4. So this full bipartite graph will have the example of graph with maximal number of edges, and also you can try to prove that this is the unique possible graph on n squared on n vertices, such that we have n squared over 4 edges and have no triangles inside of it. Okay, let's continue. And so the next problem is a generalization of the first problem. What is we restricted to have no graph isomorphic to Kn? And it's maybe not n, but maybe m or l. I know how to. There, r plus 1. So we want to again ask yourself a question. So suppose the graph G on n vertices has no r plus 1 clicks. So it's no subgraph isomorphic to Kr plus 1. What is the maximal possible number of edges this graph can have? So can we calculate the what should we do? So what can we write here? And as I mentioned before, we just can denote this by xn of Kr plus 1. So we already know that if we take complete graph of 3 vertices, which is triangle, we can prove that this is n squared over 4. But what happens if we consider the bigger n, bigger r? And the answer is the famous known two runs theorem. Again, I just don't remember the actual year. What can we prove? I suppose it is kind of notice, but maybe I'm wrong. I will check it during the break. And he constructs some example of graph called Theorem's graph, which is similar to the bipartite full graph, is the extremal solution to this problem. So it is the graph with maximal number of edges possible for graph of an n vertices which doesn't contain any subgraph isomorphic to k r plus 1. And from this we can find this number. So if graph if G is graph on n vertices and maximal number of edges such that it doesn't contain subgraph isomorphic to kr plus 1, then G is Theorem graph on n r plus 1. And what is Theorem graph? So it is a special kind of graph similar to the bipartite situation, but when we have bigger R, we need to do the same things, but in arbitrary situation. So what is the maximal possible situation where you don't have R plus 1 clicks? It means that you have some kind of vertices without. So this is part that in this independent sets. By this I mean that they have no edges inside them, but they are all connected with all other parts. So these are not bipartite graph, multipartite graph when you have different parts, and we provide all possible edges between every two of these parts. And so if it doesn't contain R plus 1 click, it means that we have exactly R different parts. So we have R parts, and we need to divide the n between them, and we want to have them to be almost equally. Because so if n is divided by n, then we have each of these parts containing of n over r. But if n is not divisible by r, then we need to sum of them containing the maybe some of them will contain on one vertex more, such that the sum of them will be equal to n. So if we have exactly two parts, then this will be full bipartite graph, and we'll have them to be so the sum of them so there will be two of them, and one of them either will have n over 2 and n over 2, the half of n, or there will be n over 2 minus 1, and then over 2 minus half and plus half. But if we have bigger number of n, then we need to distribute n over these r parts almost equally. So some of them will be having parts equal to n over r, the integer part of it, and some will be the n over r plus 1, and the number of plus 1 parts will be the same as the residue of n over r. So if I divided n over r with some kind of residue, I don't know, alpha is from 0 to r. Then we have exactly alpha parts where we can do this +1. And so it's kind of tricky to calculate the whole number of edges of the. This is the definition of Turon graph, and it's maybe a little hard to calculate the possible number of the number of edges in this graph, but we can do it. So what is the number of edges of Turon graph? You can just try to calculate, and then I will do it in a minute. I just want to check the. Yeah, so it's not 3641. And also, yeah, I misprinted. So actually, this graph, I suppose, is denoted by T of nr, not just T of nr plus 1, because just have maybe some easy, just the definition. So because we divided over r. Yes, so can we make the easy calculation? So if we denote it by n, so if we put n equal, n is equal to qr plus alpha, it means that our we have so some parts will have q vertices, some parts has q plus 1 vertices, and plus 1 we have exactly alpha part, and so the q will have r minus alpha parts. And so we just can calculate the all edges inside this part, all edges inside this part, all edges between them. So for example, if we all edges inside this part, it means that we take the two parts, which can be, we can do the r minus alpha, choose two options, and then the number of edges between two parts is just q squared, yes? Because we take each of q edges, q vertices, and connect this with other q vertices. Then we add the alpha choose 2, again choose 2 of these parts, times q plus 1 squared. And then we add the number of edges between them, which is, we take one of this part, we take one of this part, which is r minus alpha times alpha, times the number of edges between them, which is just the direct product of q times q plus 1. Yeah, so this is not a very pleasant formula, and we just need to change. So we just need to, if we want to be take a formula using only n and r, we need to take q as the integer part of n over r, and alpha is n minus n divided by r integer part times r. So it is not very pleasant formula, but we can just try some. So the asymptotics will be similar as we have k. So we can assume that we have the equal number of parts here, and so the number of edges, these additional edges, will have the don't have. So they will be disappearing in asymptotics. But okay, let's first prove the theorem, and then we'll have a break, and then we'll discuss the asymptotics, and maybe we'll just take some. If we have much time, we just can take some similar external problems. Maybe not the complete graph K R, but maybe some different graphs. Okay, so let's prove the theorem. So we want to prove that if we we take the graph without r plus 1 clicks, which have maximal number of edges, that it will be a Theorem graph T of nr. So suppose G is graph on n vertices, has no r plus 1 clicks, and has the maximal number of edges, with these two conditions. Let's do the following procedure. We will try and deconstruct this graph. So we will be taking, we will change of this graph such that the number of edges can only increase, and we will have see that it will be satisfying these restrictions. So first of all, suppose we have two vertices which are non-adjacent to each other. Suppose we have two vertices which are not adjacent to each other. So we have no edge between them. This means if they have no edge between them, then we can just look at the degrees, and if the degree of they have different degrees, then we can just change V by the duplicate of the vertex W. So we just take V as duplicate of W. What do you mean by duplicate? We just look at the vertex W, look all the edges that have the edges to some different vertices, and we just add new vertex W tiled such that it connected to the same and connected to the same vertex as W tiled. So now we have bigger number of edges because we changed our vertex V. So we omit the vertex V, get rid of it, and then change it by the W tiled. And now we have new graph. It doesn't contain r plus 1 clicks, because if the click contains W tiled, then we have the similar click containing W. And so if we have if graph G doesn't contain r plus 1 clicks, then new graph also contains double 1 clicks, and we have bigger number of edges. And so from the maximality, we can achieve that all the non-adjacent vertices has the same degree. So we can, if we change G on G tiled, which is G minus V with W tiled, then G has no r plus 1 clicks, and number of edges of G tiled is bigger than number of edges of G. So it contradicts our assumption of maximality of graph G, and from this we can assume that all non-adjacent vertices have the same degree. Okay. Okay, so if you can look closely, you can see that we're just trying to construct the Theorem graph here. So we just now we know that all the edges that non-adjacent that have the same degree. Okay. Second option. Suppose we have three vertices V, W, and U, such that V and U have edge between them, and VW and WU are non-adjacent. So we have two pairs of vertices without edges, and we have edge between V and U. From the first, we have that they have the same degree. So the degree of V is the same as degree W, and the W, and the degree of W is the same as degree of vertex U. And now I want to have, again, change the graph such that we have no edge between V and U. We have the bigger number of edges, and we will still have no r plus 1 clicks. Actually, maybe have written something where I have it. Yeah, so what we can do in this situation? We can, so if we have edge between V and U, it means that V and U have, so if it is D, then they have D minus 1 connection to other part of the graph, and W has D connections to the other part of the graph. So let's again do the same trick, but change V and U as a duplicate of W. So we have W. We make the W1 and W2 the duplicate of this vertex, and then change. So we change our graph into graph without V and U, but with W1 and W2. what happens? This new graph has no r+1 clicks because, as in the previous case, if it has r+1 click containing, for example, w1, then of course we have the similar clicks that containing w. And the number of edges now only can increase it because we have so in this picture we will having d plus d minus 1 plus d minus 1 plus 1 edge, which is 3d minus 1, and now we have 3d edges. So we again increase the number of edges, and now in new graph, so we change this situation where we have three vertices with only one edge. We change it on 3 vertices which are formed independent set. So they have no edges inside of them. So if we do first and second step many times, we can achieve that. Maybe I continue here. Oh no. So now we have so G has now two properties. First of all non-adjacent vertices has the same degree. Non-adjacent vertices has the same degree and forms anti-click. It means that if we have non-adjacent vertices, so we can say it is the same. We can say the same in different terms. We can say that non-adjacency will be the equivalence relations. So if we make relations that V is equal to W if and only if they are non-adjacent, then this is equivalence relation. Equivalent relation. So the vertex is not adjacent to itself. If V is not adjacent to W, then W is not adjacent to V. And the transitivity rule is coming from the second property. So if we have no edges between V, W, and W and U, then we can assume that we have no edges between V and U using then by 2 we have no edges between V, W, and U. So from this we have the equivalence classes, and so our graph will be having the same construction as Theorem's graph, where we have these anti-clicks, and of course so now we know that we have some anti-clicks. They have the same degree in each click. The same degree in each of these clicks. Oh no, sorry. So now the following question is, why are they need to be so first of all, they connected all with each other. So all this, remember that we have a equivalence relation, which means that so we have all edges between all vertices that we have in different clicks. Because if there are no edges between some of these two parts, then these two parts are the same by the equivalence condition. And so this is very similar to the Turon graph, but we need to be sure that they are of the same number of, they have the same number of vertices into each of these cliques. So we have similar construction, but now all we need to do is just to prove that. So if we have two parts differ by 2, for example, we can just change them such that they have more number of edges. And so this is just the property that if we have k versus here and k plus 2 here, then we have, so we need something, do something like this. So we have k plus k2 edges here, but we can change it by k plus 1 times k plus 1. And now we have bigger number of edges. This is because k squared plus 2k plus 1 is more than k squared plus 2k. So if, for example, if we have two parts differ by 2, then we can change them by two parts that are the same and have more number of edges. Because and we don't consider other part of graph because all of these vertices are connected with every possible vertex in other part of graph. And so we doesn't change that edges. We change only edges between these two parts. And of course, if we have parts of different sizes, it is better than if we want to take maximal number of edges, we want them to be as equal as possible. And so from this, we can be assured that each two of these parts have either the same number of vertices or they differ by 1, which means that we have exactly the situation in Turon graph where we can where all the parts have so that some parts will have k vertices and some k will have k plus 1. And of course, if we have no r plus 1 cliques here, then we need this part to be exactly r. So we have exactly okay. Any questions? Yeah, so maybe the last statement is not very clear because why we have exactly our parts, but we can just do some kind of trick here because if we have the, so we know that if we add one more edge, so if we take maximal number of edges, but we know that if we add one more edge, then we will have k r plus 1 inside of it. And of course, if we have less than r parts, so for example, if we have only two parts, of course, we can just provide an edge inside one of these parts, and we don't have k r plus 1. So we need, so if we have this restriction, so if we add one more edge, then we have k plus 1, which means that we have these parts can be exactly r because otherwise we can provide additional edges. Yeah, okay. So we prove that Theorem theorem. I think we'll now have a break, maybe, I don't know, 15 minutes, and 15-20 minutes, and after that we'll just, so I can just give you some additional tasks. So we just want to find, can we prove that so we just consider the complete graph and the maybe we can prove some restrictions, like for the cycle of legs 4, or maybe for the bipartite graph K is 3, 2. But I don't know, Mika, I think it's not very easy. So maybe you can think of it, and we can just maybe I will give you a hint. So you can think about it during the break, and then we'll continue. So for example, for the first one, it will help you if you prove that if G is bipartite, then doesn't contain C4, then the number of edges is not greater than the half of n to the power 3 over 2. And then we need to prove that in each and the second part is if G is graph on n vertices, then it contains bipartite graph with edges. So in each graph we can find a bipartite graph that contains none less than half of these edges. And so if we take 1 and 2, then we immediately hold the first inequality. Okay, but so maybe think about the first problem, and we can discuss it after the break. Okay. So for the first problem, I suppose that the main idea is so we want to consider any bipartite graph. So we have n is equal to, have 2 parts. I know if I need to have denotations the number of elements in this path, maybe parts, maybe. But we have all the edges between them. No, not all the edges, just some. Sorry. Yeah, we have 2 parts, and then we can find the restrictions of. Somehow find the restrictions. This graph doesn't contain the C4. What does it mean? Doesn't contain C4. This means that if we choose 2 different vertices into one of the parts, it means that they don't have pair of common neighbors. So if we have the pair of common neighbors, it means that we have cycle of 4 vertices. And if all the neighbors are pairwise distinct, it means that it doesn't contain C4. What does that mean? So we can find the, so if we take V and double V from one part, they don't have more equal to common neighbors. And from this, we want to try to make a restriction on the number of edges. So it means that if we just try to calculate all the possible pairs on the vertices from one side. So if you have, for example, I don't know, do I need to have a denotation? Maybe so we have like m and n minus m. It means that if we have only m choose 2 possible pairs of vertices, and they all covered by the vertices from the other part. So each vertex here, so if the vertex here has degree d, it means that it is covering the d choose 2 pairs of vertices. And so if we calculate, so if we have restriction on the degrees of the vertices, then we have we have a restriction on the degree of the vertices such that these degrees cannot be bigger than m plus 2. And from that we can just make some restrictions. So let's denote by the let's denote by d1 etc dn degrees of vertices, and then just try to construct some estimation. So we from this observation, so if you don't have as if a cycle on for vertices, then the sum of dk choose 2 cannot be bigger than n minus m choose 2 plus m choose 2. Yeah, so if this sum is exceeded this sum, it means that we have 2 vertices which have 2 common neighbors. The neighbors we have 2 common neighbors, and then this contains the C4. So from this, we will achieve this restriction. And now we want to just do wrote some inequalities such that we can achieve. So we want to from this get that 4e squared is not greater than n cubed. So if we can achieve that 4e squared is not greater than n cubed, then the number of edges will be not greater than half of n to the power 3 over 2. Okay, so let's, if you want to look at degree, E is just the sum of d1, etc., dk. So we want to connect this with decay choose tool. So let's just make some calculation. Decay choose 2 is decay times decay minus 1 over 2. So if we take 2 decay choose 2, it will be just decay squared over 2. Sorry, just decay squared minus decay. Sum of these guys, 2 sum of decay choose 2 is sum of decay squared minus sum of decay. Okay, so from this we can achieve that sum of decay squared is equal to sum of decay, which is E, plus 2 sum of decay choose 2, which can be restricted as E plus 2 times n minus m choose 2 plus m choose 2. So is it right? Yeah, okay, so yeah, there's a little mistake here, sorry, because number of edges is not the number of degrees, but by the handshaking lemma is the half of the degrees, so there will be just, so here it will be 2e here, so I need to write 2e here. And also this will be just the sum of the squares of d1 plus dk squared. Okay, so if we continue here, so we just look at proof that sum of dk squared is not greater than 2 of e plus n choose m over 2 plus m choose 2. So here I just calculate the number of edges of bipartite graph plus the maximal number of edges in one part plus maximal number of edges in second part. So this is not greater than 2 times n choose 2, which is n squared minus n, which is less than n squared. So from our conditions that our graph doesn't contain C4, we can obtain the sum of the squares of degrees is not greater than n squared. And then we just need to have, so if we need to prove inequality, we need to prove that if we take the square sum of the decays, then it is not bigger than n times sum of dk squared. And then we can prove that it is not bigger than dq from this one. Deep some of you may be known this inequality. Can we just, is it correct? Oh yeah. You only find my mistake. Okay. Can someone explain me what is the inequality of? Is it true that sum of square of sum is not bigger than a number of summands times the squares? Yeah, it's some kind of Cauchy inequality. I don't know if you're familiar with this. So usually they're written in some maybe different form. It's so we have quadratic mean and arithmetic mean, and we have the following inequality. Yeah, so maybe we'll just so we have so we have some kind of this inequality, and this is the same, but we take square of the first. So if you take square of the first on the both handles of inequality, then we will have the both parts of inequality, then we achieve this guy. Okay, so we prove. So again, it's external problems. They have this complexity that we need to use some. So this idea is kind of obvious that we want to. So we just have the strict restriction over strict conditions that we don't have before. And then we just take some inequalities using some tricks, and we achieve that for E is not greater than n cubed. But now if we want to prove it for arbitrary graph, we need to prove some similar problem. We need to prove some type of problems of bipartite graph. How many edges can bipartite graph have in our graph? So we need to find this following statement. So if you have graph G on n vertices, then there exists H bipartite graph in G such that the number of vertices in G is at least half of the number of vertices in H, at least half of the number of vertices in G, and from this we can achieve this our external problem, because if we have a vertex, we take the bipartite graph which have at least half of the vertices, and from it we can have that that A of H is not greater than n3 cube over 2, and so 2E of H is not greater than n to the 3 over 2, and this is bigger than number of edges in G. So we have the inequality that we need to achieve. Okay, how do we get bipartite graph which contains the edge of at least half of the edges from our graph? The trick of this exercise is again the idea that the ideas that we have met already is just consider the maximal possible situation, write the condition which that graph doesn't contain the following subgraph, use induction, and now again the idea that we already met before, the idea of double counting. So we want to, what we want to find? We want to find some two parts in graph G. We want to dissect this into two parts A and B, such that there are many edges between A and B. At least half of the edges are between A and B. And so, for example, we want to have, to be sure, we want to have some, we just take some vertices from the set of vertices and just want to calculate the number of edges that goes outside from A. If the edge that has only one endpoint in the A is big enough, exactly is more than half of the edges, it exactly means that we have find our partition into two parts. So we find the graph H. So all we need to do is somehow calculate, somehow find the subset of set of the vertices such that there is many edges coming outside of it. And from this we can just try to achieve it by double counting. So let's look at all pairs. So look at all pairs of AX such that A is a subset of the set of the vertices, X is some edge, and only one endpoint of X belongs to A. Only one endpoint of X belongs to A. Okay, so we have the set of all such pairs. We have the number of all such pairs such that this restriction, with this restriction. Let's calculate the number of all pairs. If we fixed, let's fix the edge. So let's sum of this. Let's sum of possible pairs where X is from the edges. So if we fix the edge X, how many possible subsets of A of vertices we can take such that only one endpoint of X belongs to A? So how many A's are there? So we want to calculate all the subset of the vertices such that they have only one endpoint of X. It means that they either doesn't contain V or either doesn't contain W. So they either contain one of the endpoints of this X, or they doesn't contain the other endpoint of the X. And so how many subsets can we get here? So we can take, we want to calculate all the subsets of the, so we have n element set. And we want to collect all the subsets that doesn't contain two elements of this, they contain only one element of the set. So they either contain one or two, but not one and two. So I think this is maybe obvious because we just took one or two and then took one of the all other elements, which means that there are 2 to the power n minus 1 possible subsets. Yes, because we can take all possible subsets of n minus 2 element set and then add v or w, and so we have twice this number of sets. Okay, so this will be 2 to the power n minus 1 times the number of edges. So we have so if we summarize by the all possible subsets, the number of pairs of A and X such that with the following restrictions, then it will be it is equal to 2 minus 1 times E. And we have here 2 to the power n summons. By the pigeon principle, we obtain that there exists a subset A such that this is more than the average, which means that it is exactly E over 2. And E is number of edges in our graph G. I just need maybe rows. Here's okay, so we do what we need. We want to find a subset of A of vertices such that the number of edges that's going out of A is exactly the half of the, more or equal than the half of the edges in graph G, which is exactly the situation that we want to achieve. So we have more than half edges going out of A, so we can take A is the first part, V of G minus Z minus A as the second part, and so we have find two parts such that the edges between them are covering the more than half of the edges of in our graph. And from this we can achieve this restriction on graphs without cycles of length 4. So you see this is not very maybe not very easy, but we can achieve some restrictions. Okay. I know we have much time. Okay, so we just yeah, so if you have any questions, I think you have 2 minutes to asking questions, and then we will start our test in 2 minutes, I suppose, if you have no questions. Okay.